For most trace bases of the trace space of the symmetric group, we have an explicit formula for how to evaluate the trace, every element to that trace basis, add every element to the symmetric group. That is, we can do that for every trace basis except for the basis of irreducible characters, which is the most important basis. So, in addition to looking for explicit formulas, we could look for generating functions. So we have the immanence, and we have some nice forms for immanence corresponding to induced sign characters and induced trivial characters, but we don't have a nice form for the immanent corresponding to irreducible characters. Now let's look at a different type of generating function that might help us evaluate traces at elements of the symmetric group. So let's say we have a basis theta lambda. Let this be a basis of the trace space of the symmetric group. So we can compute theta lambda of W. Let me say theta lambda of V for all V and Sn with an immanent if this expression has a nice form. So we know nice forms for the induced sign characters and induced trivial characters. Another idea is let's fix the element of the symmetric group and let the partition vary. Now, the symmetric function is sum over lambda theta lambda of V m lambda records all of the evaluations theta lambda of V where theta varies over all partitions of n. So here we're fixing lambda and letting V vary over all elements of the symmetric group, and now we're fixing V and letting lambda vary over all partitions of n. And I guess we don't have to pick monomial symmetric functions here. We can pick any symmetric function basis we want and pick out the coefficients of those. And this would be useful if it has a nice form. That is, if we don't have to know the coefficients before writing it. If we can write a symmetric function by some other definition and have the coefficients pop out, that would be nice. So let's define capital Y of V to be the symmetric function which has induced sign characters evaluated at V, the induced sign character indexed by lambda, next to the monomial symmetric function m lambda. And it turns out that we can get all of the trace evaluations that we care about from this symmetric function. So we can get chi lambda of v, eta lambda of v, even phi lambda of v and gamma lambda of v, etc. And to see how these other trace evaluations are related, we need to look at transition matrices between different trace bases, or equivalently between different symmetric function bases of the Z module of homogeneous degree n symmetric functions. The symmetric function basis transition matrices show how this is possible. Now recall that we have, if we want to express Schur functions, actually power sum symmetric functions instead of Schur functions, in terms of Schur functions, we have p lambda equals a sum over mu chi mu evaluated at any permutation of cycle type lambda s mu. And actually the inverse of this formula is almost the same. S lambda is a sum over mu chi lambda of anything in the mu cycle type conjugation class all over z mu times p mu. Where, to define z mu, let's say if mu equals 1 to the alpha 1, 2 to the alpha 2, so this many 1s, that many 2s, etc., that many n's, then z mu equals, well, this number interpreted as integers times the product of the multiplicities factorial. So here this is multiset notation. This many 1s, that many 2s, etc. And this is actually 1 to the alpha 1 power, 2 to the alpha 2 power, etc. Right, so these are Frobenius formulas for the transition matrix between power sum and Schur functions. We also have, now you could spend 2 weeks doing all the transition matrices between all the different bases of the symmetric group, but I don't want to do all of them, so I'm just going to state without proof. So S lambda equals, we know an interpretation for the coefficients of the monomial subvector functions and the monomial expansion of the Schur functions. So these numbers are called Koska numbers. And k lambda mu is the number of semi-standard Young tableau of shape lambda and content mu. Now these numbers occur as a transition matrix between the monomial basis and the Schur basis, but they also appear in transition matrices between other bases too. So if we expand the homogeneous symmetric function in terms of the Schurs, we get the Casca numbers coming up slightly differently. So the index on the Casca number is swapped from what it was in this case. So the first index matches this basis, and the second index matches this basis out here. And then if we write the elementary symmetric functions out, those are related to the Schur function also by Casca numbers, but we need to transpose the first index. And the omega involution shows that these two are the same. And also, if we want to expand the Schur function in terms of forgotten symmetric functions, then this is the equation we get. And this is equivalent to the original equation we know, also by the omega involution. Alright, so if we define this symmetric generating function y of v to be a sum over lambda partitioning n, epsilon lambda of v m lambda, then we also get in the forgotten basis eta lambda v f lambda. And if we expand it in the power sum basis, we get negative 1 to the n minus length of lambda psi lambda of v p lambda all over z lambda. And if we express this in the Schur basis, we get irreducible character indexed by lambda transpose evaluated at v next to the Schur function s lambda. And if we expand this in the elementary basis, we get phi lambda of v, so that's the monomial trace, next to e lambda. And if we express that in terms of the homogeneous basis, then we get the forgotten trace evaluated at v next to the homogeneous symmetric function h lambda. Now, it's actually easier to prove this if we apply the omega involution to y of v. So equivalently, omega y of v is equal to, so the monomial symmetric functions go to the forgotten symmetric functions. So epsilon lambda v now is next to forgotten symmetric function f lambda. And then f lambda goes to monomial symmetric functions, so the induced trivial character now appears next to a monomial symmetric function. And the involution acts on the power sum functions by multiplying by a power of -1. Actually, it's going to get rid of this. So we get psi lambda of v p lambda all over z lambda. And then the Schur function gets mapped by omega to a Schur function indexed by the transpose partition. So these two partitions are going to be the same instead of being transposed of one another. And the elementary symmetric functions get mapped to the homogeneous symmetric functions. So we'll have monomial trace evaluated at v times h lambda. And finally, the homogeneous symmetric functions get mapped to the elementary. So we get forgotten trace of v next to e lambda. So let me call this equation here star. And we'll prove this one. All right, let's consider, we've got a lot of sums here. Let's consider the second and the fourth sums. So the one with the induced trivial characters and monomials, and the one with the irreducible characters and Schur functions. Now, in these two sums, the traces and the symmetric functions satisfy. Let's see, so the traces are, we've got induced trivial character related to irreducible character. And we know that they're related by Cauchy numbers. And the Schur function is also related to the monomial symmetric function by Cauchy numbers. So in particular, we have S lambda equals a sum of K lambda mu M mu, and I'm going to write chi mu equals a sum over lambda K lambda mu chi lambda. So now we can see that we've got the same Cauchy numbers in both places. Let me erase the first part of the claim. If we do the second part, then omega is just going to prove the first part. Now let's expand this fourth sum in the monomial basis. So we've got sum over lambda chi lambda of v SV, and instead of SV I'm going to write sum over mu K lambda mu M mu. Then if I take this sum and put it on the outside. So the sum over mu first. And then take the sum over lambda, and I'm going to pull this k lambda mu as far to the left as I can. So I'll put it right here next to the sum over lambda. And then we have chi lambda of v and mu. And if we look at this inner sum, this is exactly what we wrote up here for eta. So this is a sum over mu, eta mu of v and mu. So that means that the fourth sum is actually equal. This is the second sum. The fourth sum and the second sum are equal. So this comes from expressing one trace in terms of another and one symmetric function in terms of the first one using exactly the same transition matrix. This actually works for all of the other sums when we compare it to the irreducible character sure sum. So similarly, for each of the remaining sums, so in each case we have a sum over lambda, some trace, evaluated at v, and then some basis. Let me write t lambda. So for each other sum, there's a matrix. Let's call it b lambda mu, because I used a for the forgotten monomial symmetric function transition matrix. Let's say b lambda mu. An equation is just like this, where we've got S equals b lambda mu t mu and theta mu equals b lambda mu chi lambda. So each of these sums is related to the fourth sum. Related to the fourth sum, and then we can do the same thing here. So in particular, the coefficients b lambda mu are given by Cauchy numbers with the first partition transposed, irreducible characters, and then inverse Cauchy numbers, which are just entries of the matrix that's inverse to the Cauchy number matrix. So we have 1, 2, 3, 4 other sums. So we did the second. So it's the first, the third, the second to last, and the last sum, which are related to the fourth sum this way. So again, that proves this expression for omega y of v, and then applying omega we get the first expression. I should say we get the claimed expansions. For y of v. And again, the motivation is, I guess I can say this is a corollary. If we can find a combinatorial object let's say g of v, this could be a post set or a planar network. And if epsilon lambda of v equals the number of something that we can count in g of v, then maybe g of v can help. Maybe we can count something else in g of v to perform the evaluations of irreducible characters, induced trivial characters. Those are going off the board. So with the evaluations of all the other traces at v. So maybe chi lambda of v, psi lambda of v, eta lambda of v, gamma lambda of v, and phi lambda of v. So we're gonna find such a combinatorial object sometime in the future, and we're going to use that to do some of these evaluations. The end.